as our example. When you run a proton NMR, what's your typical window? 0 to 10 parts per million for most organic things, maybe up to 12 if you're interested in carboxylic acids, down to -2 or 3 if you're interested in more obscure aromatic things, maybe up to +15 if you're starting to get a little bit more exotic, wider windows for more organometallic type structures, but just to make...
Or stuff from the Hoff lab or the Higgs lab.
But just to make the math easy, let's just pick 10 parts per million as our window. Okay, parts per million means literally parts per million. So 10 divided by 1 million times 300 million hertz means that you're acquiring spectra over a window of 3000 hertz, which means that your proton NMR experiment, all of your protons, most of them anyway, all the ones that are between 0 and 10, are resonating between 300 megahertz plus or minus, so 300 million hertz plus or minus 1500 hertz. So in other words, your error there is very small, right? To a first approximation, that thing that I set up at the top, all protons resonate at the same frequency. To a first approximation, that's true. And again, it's amazing that NMR actually works as a useful technique when you think how tight all your electronics need to be in order for that experiment to work, how much control you need to have over the entire process, I think is really remarkable. For carbon, of course, it's more or less the same story, although the window is a little bit bigger as a proportion of the average signal. So in the carbon spectrum, typically you're dealing with a 0 to 200 parts per million window. Again, you can go a little more up or down, but 200 makes the math easy. You're dealing with a window of about 15,000 hertz, which means that your carbon window overall is 75 million hertz plus or minus 7,500. Pretty small as a proportion of the average signal. It's amazing that NMR spectroscopy works. Okay. Any questions about that? Kind of makes sense where the numbers come from?
Jeremy, I couldn't understand where the 1500 and the 7500 number came.
Oh, so I just divided this by 2. So the total window is 3000 hertz, right? That's just...
Oh yeah, I see.
So if that's 3000 hertz, is your 10 ppm window. Somewhere in the middle, let's say, is 300 million hertz. 1500 this side, 1500 the other side.
The middle is also known as your carrier frequency. You ever hear the term?
Okay. So, very small differences in the magnetic environment around your nuclei of interest make each proton, or carbon, come into resonance at a slightly different frequency. Slightly, very slightly different frequency, but enough to be spectroscopically useful. And ultimately, this is why NMR is able to give you some useful information. In other words, more than one peak, all the coupling information, everything that makes NMR good comes from these very small magnetic differences. Okay. Typical windows, again, in the carbon spectrum are sort of 0 to 200 or thereabouts. In the proton, maybe -5 to 15, everything's 0 to 10. Okay. Decreasing frequency, increasing field, decreasing field, increasing frequency. Okay. Now we're going to talk about where those shielded and deshielded terms come from. And because I have to tell you somewhere, I'll tell you on this slide, there's no absolute 0 in a proton NMR or in a carbon NMR. The numbers that we write at the bottom of the spectrum are always defined with reference to some kind of standard. Okay? For historical reasons, for both proton and carbon NMR, tetramethylsilane was used as the additive that you would actually drop into your NMR solution. Okay? And that was just convenient.
It's actually now the official standard for all nuclei.
Oh, so everything else is referenced back to tetramethylsilane?
The new recommendations for even carbon is to use the Chi scale instead of ppm.
Oh,
Nobody does it.
no.
And I mean, the IUPAC group was a bunch of NMR people, and we
Yeah.
recommended it,
Huh.
and except for exotic nuclei, we're still using ppm.
Yeah, no, everybody uses ppm for when not so much appropriate. So the reason for that is because tetramethylsilane is mostly out of the way of most of the peaks that we're looking at in the proton NMR, because it happens to come in at 0. Well, 0 is defined relative to it, but it happens to come to the right of most of the protons that we're looking at. And because tetramethylsilane doesn't react with stuff, so it doesn't react with other molecules that are in your mixture, mostly. Okay. Nowadays, of course, you don't physically add tetramethylsilane. You usually reference based on the residual proton peak in your NMR solid. But that's where the numbers come from. Okay, so where does chemical shift actually come from? Why do we have these differences in resonant frequency? There's a few things. We're going to start by talking about the inductive effect. Okay. So in a magnetic field, the electrons around a nucleus are moving around, and they're setting up a secondary magnetic field that opposes the applied magnetic field at the nucleus. So, what does that mean? Nuclei that are in a region of high electron density, lots of electron density around, are going to experience a weaker field because they're being shielded by the applied magnetic field. Okay. That means that you're going to need to give a little bit more field in order to bring them into resonance. Remember that back in the old days, when we were doing continuous wave NMR, we were actually moving the field. So if you've got a nucleus, not to scale, okay, and it's got a whole bunch of electron density around it, it's shielding it from the effects of the applied magnetic field. You want to bring it back into resonance at 300 megahertz, let's say. You need to apply a little bit more field in order to make that happen. Okay, bring them back into resonance. So we say that these nuclei are shielded, and on your spectrum, these are going to appear at a low chemical shift number, which we give the symbol delta, Greek letter small d. Okay? By comparison, conversely, nuclei that don't have very much electron density around them, have less electron density than your average nucleus, will resonate at a proportionately lower field, and we say that these nuclei are d-shielded. In your spectrum, these are going to appear at a high chemical shift number. It's very backwards, I know, but that's what we get when we have history. We're stuck with it. Okay? So, let me prove to you now that this works, because I think this is really cool. We think of chemical shift numbers as kind of arbitrary sometimes, but this is really where this is coming from. So let's consider a series of methyl groups attached to a bunch of different elements. We'll work from electropositive to electronegative. Fluorine is more electronegative than oxygen, is more electronegative than chlorine, is more electronegative than a hydrogen atom, is more electronegative than lithium. Right? Everybody probably knows your electronegativity series. And if you don't, there's a periodic table on the next page. Okay? What that means is that we get proportionately more and more and more de-shielded as we're pulling more electron density away from those protons. Okay? Pulling more electron density away, we are de-shielding the protons. We're moving to higher chemical shift numbers. It's cool, right? I think it's cool that it actually works. Like it's legitimate. I don't know if it's linear, but it seems cool.
So NMR and chemistry actually match.
Yeah. This tells me that electronegativity is real, or that everything that I've written at the top of the slide is real. I just think that's fascinating. I think it's fantastic that it works. Just give people a minute to write down stuff. Okay. changed that on my version, but it didn't, the change didn't take effect. Did it on yours? Yeah, I fixed it on yours. Anyway, it says the same thing, it just made more sense on your version. So, because it's easier to think of things being electronegative than electropositive, that's usually the way we talk about them. So, carbon, yeah, my periodic table doesn't show up here either, I must have forgotten to hit save. So if you look on your periodic table, which is on your version but not on mine, or you remember your electronegativity values, you know that carbon is more electronegative than proton. Okay? So that means that every time you take away a proton and you replace it with a carbon atom, the signal is going to move downfield. Okay, because you're pulling more electron density away by adding this more electronegative element. Okay? And that gets us to a really, really useful series. Actually, this is super useful to remember in terms of predicting chemical shift numbers. These kinds of trends are really important. So let's just focus on the carbon chemical shift for a minute. Let's start with methane. Okay? Not the world's most useful molecule, but you can take an NMR of methane for sure. You guys will see methane get generated if you're watching some catalytic cycle or something that spits out methane. You can watch it in the NMR, it's really fun. So methane, you'll see a carbon signal at -2.3. Yeah.
Yeah, no, I'm just thinking.
We don't want to guess.
Generating gases, generating flammable gases.
You can see hydrogen in the
electronic form.
You can see hydrogen in the NMR as well.
Oh,
Get
yeah,
spit out.
you can see it.
Yeah.
That's when I start shaking.
Yeah. I'm not saying that some things are better not to tell the person who owns the instrument, but anyway. So if we take away one of those hydrogen atoms and replace it with a carbon atom, so now you've got ethane, what happens? Well, you move downfield 8.4 parts per million. We replace another hydrogen with a methyl group, move downfield again, replace another hydrogen with a methyl group, we move downfield again, and finally, we've replaced all the hydrogens with methyl groups, we look at the NMR of the central carbon, let's move downfield again. Okay. This is important because when you're predicting what your NMR spectrum for a given compound might be, you might well have a comparator molecule that's very, very similar, but maybe lacks an alkyl group. So you can think, well, what happens if I were to replace that hydrogen atom there with that alkyl group? That middle carbon is going to move downfield. Really, really useful to remember this, to remember the trend and remember by about how much you're moving every time you replace a proton with a carbon. More or less, you're moving by about 8 parts per million in a carbon sense. Okay, and that turns out to come pretty close to the alpha value that we're going to talk about when we get to the additivity tables. That's where that comes from. Okay. In the proton channel, we're seeing the same thing, but the magnitude, of course, is smaller because the window is smaller in the proton channel. Okay. So we start with methane, and a proton NMR is 0.23 parts per million. We replace one of those protons with a methyl group, we're down to about 0.8. Replace another proton with a methyl group, down about 1.33, and we replace another one, we get to 1.68. So in other words, every proton that we exchange for an alkyl group, we move downfield by about 0.2 or 0.3 parts per million. Another really good thing to keep in mind when you're thinking, well, I know what this NMR looks like for this molecule, I've made a perturbation, how much is that going to change the NMR? Okay, useful to know. Pi bonds have electrons associated with them. Hopefully that's not news to you. Those electrons in the pi bond also set up magnetic fields, and these will influence the relative shielding or deshielding of neighboring protons and neighboring carbon atoms. Rationalizing these numbers based on molecular orbital properties of the nearby pi bonds is totally doable, but we're not going to do it today. It's not something that you really need to worry about too much. Really, you just need to know by how much protons shift when they're nearby pi bonds. Okay? And it turns out that in some cases the protons shift more than the carbons, and in some cases the carbons shift more than the protons. We're going to see some examples of that when we get into the sort of expected chemical shifts for sort of normal functional groups. Okay? But let me give you some examples. Here's methane again, 0.23 parts per million. Okay. If we replace one of those protons with an alkene, we move pretty substantially downfield. Okay. Considering that the proton window is only 10 parts per million wide, we've moved downfield by about 1.5 parts per million. Okay. If instead of an alkene, we put an alkyne, we also move downfield. If instead of an alkene or an alkyne, we put a carbonyl group, we also move downfield. Generally speaking, the more stuff you do in the vicinity of a proton, you tend to pull things downfield. But there's certainly exceptions to that. We're going to talk about cyclopropanes and other things that move protons upfield relative to where you might expect them to be. Okay. Protons that are directly attached to a carbon, which is participating in a pi bond, are relatively far downfield. So a prototypical alkene, like the one in ethene, for example, appears at 5.25 parts per million in your proton NMR. And we'll talk about where exactly that moves as we add different functional groups around the alkene, and as we go to allenes and other things like that. So you'll see lots of examples of aromatic systems and why that changes. You'll see lots of examples. Let me just give you a flavor of what you're going to see when we get into the additivity tables by telling you a little bit about polarized bonds. I really like these examples because we do a lot of vinyl ether chemistry in my program, so I always find this really fun. Okay. So I've talked mostly about inductive effects, and I've talked about sort of having electron clouds nearby to protons. Resonance effects are really nicely visible in both the proton NMR and the carbon NMR in really nicely understandable ways. And so your ability, those of you who have taken enough organic chemistry to be able to draw a resonance structure, can be really useful in terms of helping you to predict likely chemical shifts in structures that you've made or that you hope to make. So let's just consider this vinyl ether as an example and this enone as a second example. Okay. In the vinyl ether, we've got 2 carbon atoms, okay, both of which have protons attached to them. Okay. Neither of which appears at the 5.25 parts per million that we expect for a sort of prototypical alkene. In fact, we see pretty different shifts. 3.85 parts per million down here, 6.38 parts per million over there. So one of them has moved in the de-shielding direction, one of them's moved in the shielding direction. Why might that be? Well, let's draw a resonance structure for a vinyl ether. We'll take the electrons that are present on the oxygen and pump them into the pi system. We can draw a resonance structure that looks like this. What happens when we do that? We build up negative charge on that carbon. What's the effect of that negative charge? It's to shield these protons from the applied magnetic field. As a result, we need to apply more magnetic field if we're doing an old continuous wave NMR. Okay. That moves in the upfield direction on our proton NMR. All the way from 5.25 all the way to 3.85. That's a lot. It's weird to see an alkene at upfield of 4 parts per million. That's what we get with these kinds of really electron-rich systems. You'll notice that in the resonance structure that I've drawn, nothing's really happened to that proton. Okay. So resonance effects aren't really perturbing this proton. What about inductive effects? Oxygen is more electronegative than is proton. Okay. And so we're pulling electron density, that's that little purple arrow, I don't know if you can see it there, little purple arrow, pulling electron density away from this carbon. And so whereas these protons were shielded, this proton is de-shielded. And that beautifully explains that at least the directions of the shift for all these protons in the vinyl ether, which I think is really cool. Again, chemistry is real, right? We get this direct readout of the chemical properties of the molecule by looking in the proton NMR. You can actually use the proton NMR chemical shifts, if you're very careful about things, to predict things like nucleophilicity of a series of functional groups, as long as you're all comparing within the same kind of series and not jumping around too much. What about the enone? In an inductive sense, that carbonyl group is electron withdrawing. And so this proton is going to be a little bit de-shielded. moves downfield from 5.25 in a prototypical alkene to 5.85, a little bit deshielded. But if we draw the resonance structure, we can see that this carbon is really, really deshielded, okay, because it's got sort of a full positive charge in this resonance form at least. And so this one moves downfield a little bit, this one moves downfield a lot. So if we know simple resonance structures, we can draw an idea of what the properties of the molecule are going to be. We know a little bit about nucleophilicity and electrophilicity that allows us to predict the chemical shift directions, at least, if not necessarily the magnitude. Okay, does that make sense? Any questions about that? Okay. I love that example. Super. Okay, one more thing that I want to show you. And this is another thing that I think really validates like what we tell people in second year organic chemistry. It makes me feel good to see this. Chemistry is true. In a pi system, we have a ring current. We have electrons that are essentially circulating through all of the p orbitals, well, through the molecular orbital that's comprised of all of the atomic p orbitals in a pi system. Okay. Anytime you have circulating electron density, you have a magnetic field. Right-hand rule or left-hand rule, depending if you're a chemist or a physicist. Don't worry about which way it goes, but you have a magnetic field anytime there's a movement of electrons. A magnetic field even associated with electrons running down a wire. It happens that the magnetic field looks like this. Sort of the magnetic field that you would have the same for an electromagnet. Basically a benzene ring is a little electromagnet. That means that outside of the ring, any protons or carbon atoms or any other nucleus that finds itself outside of an aromatic system is deshielded. Anything that finds itself inside of an aromatic system is shielded. You can see some really nice effects here. First of all, just benzene itself. If you consider this to be a simple alkene, you might predict that that proton would come in somewhere around the 5.5 mark. But it's clearly not. It's moved downfield by a good almost 2 parts per million from what you might expect it to be. So clearly there's something going on here, and that something is the aromaticity, the magnetic field outside of the aromatic ring, moving that proton downfield. So aromatic things, generally speaking, come in more downfield than simple alkenes. But look at this crazy example. Right? This whole macrocyclic thing is aromatic. You can count up all the electrons and convince yourself that it's a 4n+2 number. Outside the ring, these protons appear at 9.2 parts per million. That's even further downfield than benzene. Certainly not what you would expect if you just considered this to be an isolated alkene. The protons that are inside the ring come in at -3 parts per million. There's even more extreme examples of that. It's pretty amazing, right? I think it's really cool. Okay, so that's where we're going to stop today. The assignment that I've given you will have you kind of work through some of the math that we've done so far today, calculating sensitivity for different NMR experiments, or the lack of sensitivity, I guess I should say, for certain NMR experiments. Have fun with them. They're going to be due at the beginning of next class. I've made a note at the bottom of your assignment. All of the questions that I've given you are trick questions, in that if you work through them based on just what I've told you today, you're actually going to come up with the wrong answer, but I think that that's okay. There's some value in coming up with the wrong answer. You might, by hunting around on the internet, find the correct answer, and if you do a really good job of hunting around on the internet, you might find the reason for why you get to the correct answer and not the wrong answer. If you don't worry about it. At the beginning of our next meeting here, we're going to work through what the right answers are and why the obvious calculation gets you to the wrong answer. Okay? Good? Thanks.